Hello, everyone. Mr. Minnick's my name. Math is my game. I'm joined today by my second period Algebra 2 class. I think they're excited to be here. It's a Monday, Tuesday kind of day. This is prerequisite material. Prerequisite material. If we looked at the book, we're in the first chapter of the book, and we're going to be kind of going into the second chapter of the book here with this stuff. Today, there's a few things we're going to be talking about, and the first of which is real number properties. Real number properties, as opposed to what? Fake number properties? No. These are properties that pertain to the real numbers. Now, if you missed last week we had this big hierarchy of number discussion. We said that the most specific type of numbers, anybody remember what it was from last week? The most specific subset of numbers was the 1, 2, 3 natural or counting numbers, and then a step out from that would be where you add 0, the wholes, etc. So if you missed that lesson, you'll want to check it out. But all these properties pertain to real numbers. So I'm going to say this. I'm going to say let A, B, and C be real numbers. Let A, B, and C be real numbers. There's all kinds of number properties, and they have different names, and some of their names are funny, and some of them I'm going to give you a way to memorize them, and it'll make sense, and I don't mean to be perverted, but you'll never forget this one anymore. Real number properties. There's this one that says it doesn't matter what order you add two numbers in. You're going to get the same thing. It says it doesn't matter what order you multiply numbers in. You're going to get the same thing. Anybody remember the name of that property? In Northeast Ohio, we have a very difficult time saying this one. Think about your siblings. Maybe they're going to college in the fall. Maybe they're driving back and forth from home to college. What kind of students are they? Starts with a C. They're commuter students, and it's the commutative property. Nice. Good one on you. Now, when people pronounce this, say the commutative property, there's no N in it. It's commutative. Because we have stuff in the air, because we have allergies and sinuses, well, a lot of times we say the commutative. It's not communitive, it's commutative. You'll hear me say the commutative. Don't confuse that with the communist property or the Communist Party. It's the commutative property, okay? And of course, one's of addition, one's of multiplication. I'm not even going to say which one's which. I don't want to insult your intelligence. Are we doing okay so far? Good. All right. So we got one of the properties out the way. There's this other property. And I got to be honest with you. I like trick questions. Love trick questions. And I might ask you a trick question, and I'll kind of show you what to watch out for. But there's this other property, and really all this other property does is just move parentheses around. And because all you're doing is moving parentheses around, this is the abbreviation for it. Yeah, because it just says that A plus B plus C, if you group the first two first, you're going to get the same answer if you have A plus B plus C, and you group the last two first, you're going to get the same answer. And it works the same way with multiplication. If you have A times B times C, that you'll get the same thing if you have A times B times C. Okay, so yeah, because you're just moving parentheses around, that's the associative or associative property. And of course, one's of addition, and one is of multiplication. Those are the easy ones, right? You learned those in like, what, 5th grade, 6th grade? Good. Well, there's got to be more properties because we're devoting a whole entire lesson to this, and there are some. There's this one. If you ask Siri Siri will insult you. Siri will make you feel about this big about yourself. Siri will say that you have no friends, thereby calling you a loser. I'm not saying you're a loser if you have no friends. I think it's better off in life to sometimes have no friends, because friends aren't friends. They'll stab you. Anyway, I'll stop talking about that. Division by zero. Suppose we have something like a divided by zero. Now, there is an assumption that we need to make about the real numbers a, b, and c. Remember earlier I said let a, b, and c be any real number? I probably ought to clarify this. Where a is not equal to 0, b is not equal to 0, and c is not equal to 0, okay? I want to make that real clear. Because there's this thing that happens in mathematics that causes people to argue. If you have this, if you have 0 divided by 0, that ends up being the same thing as this. It kind of looks like an owl, doesn't it? It's the same thing as this, and we'll see why in a few minutes. But anyway, there's an argument that has ensued for 1,500 years in mathematics about what the value of that equates to. What happens if you divide something by itself? What do you get? 1. And if you take 0 and you divide 0 by something, what do you get? 0. And what happens if you divide something by 0? You have no friends, and Siri insults you. We better go back to this property, this property, this one I started and didn't finish. This division by 0 property. A divided by 0. Anybody remember what this is? You ever try to find the slope of a vertical line? It's undefined. Nice, good. It's undefined. You cannot compute it. That calculation cannot be made. Okay? So, back to this just for a split second. These could equal, in no particular order, because you're dividing something by itself, they could equal 1. Because you're dividing 0 by something, it could equal 0. Bless you. And because you're dividing something by 0, it could be undefined. And it's not real clear which one's the right answer. Mathematicians have debated that for 1,500 years, and they're probably going to debate it for another 1,500 years. So, anyway, let's get back to these number properties here in a minute. So we got the commutative, we got the associative, we got division by 0. There's got to be more number properties than that. Maybe we should get into some exponent rules. Well, this is a good one. Let's look at some radical rules. The square root of a times b is equal to the square root of a times the square root of b. Now, a few minutes ago, I said that a is not allowed to equal 0 and b is not allowed to equal 0. And c is not allowed to equal 0. Because of these, in this particular instance, I got to say that a is positive and b is positive also. If I didn't, some very bad things are going to happen. Very bad things. Anyway, this is called the product property. This is called the product property of radicals. The product property over 4 radicals. Okay? The product property over 4 radicals. We're going to use that in chapter 4 when we simplify square roots. Maybe you remember how to do that, how to simplify the square root of 8. And get the answer in simplest radical form. I don't want to get too far into our exponent rules, but there is an exponent rule that I think is worth looking at. And I guess it's a real number property. I'm going to call this the implicit the implicit power rule. There's certain things that are implied that you should just know, that you should just be aware of, that you should assume, and it's safe to assume it. If you raise any number to the first power, what's that going to equal? That number. Nice, good. Okay, so if you see a number and there's no exponent on it, you can assume that its exponent is 1. So that's the implicit power rule. There's a couple other exponent rules while we're on this one that it's worth looking at. The zero power rule. So if we had the number a raised to the 0th power, does anybody recall what this would equal? Somebody said it. 1. Nice, good. Not many people know the answer why. Maybe when we talk about exponents later on in the year, I'll talk about that. There's one more. We'll talk about the negative power rule. The negative power rule. The negative power rule says if you raise the number a to the negative first power, this one kind of reminds me of how I cracked my head open in a swimming pool one time. I was trying to show off, and I went to do a backflip into the swimming pool, and I cracked my head on the side of the pool. It was awful, so bad. Not a fun time. So when you do a backflip, you essentially flip over, and when you raise a number to a negative power, what it does is it inverts that number. It puts that number under 1. Okay. A lot of people think that negative exponents make numbers negative. They don't. They do make numbers smaller. For instance, if you had the number 2 and you raised 2 to the negative first power, that would be 1 divided by 2 to the first power, or 1/2. Okay? So raising 2 to a negative power doesn't make it negative, it just makes it smaller. I learned so much about exponents in this one computer class I took. Do you want to hear about it? The professor looked like Pat Morita. Now, if you don't know who Pat Morita is, Pat Morita played Mr. Miyagi in the original Karate Kid. This guy was an Asian man, about 5'5", potbelly on him, probably in his 60s, had really long hair, had a really long goatee all the way down to his knees. And this guy would stroke his goatee, and he'd waddle when he walked. And his last name was something like Jameson. It wasn't an Asian last name, but the dude looked just like Sensei. Like when he enters the room, like you're in his dojo and you want to take off your shoes and bow and stand bow, and you're just ready to go to crane stance. And this guy said so many cool things about the number 2, but when he talked, I had a hard time maintaining my composure, because he would say, "Okay, class, today we talk about computer." "Okay, fine. Everything with computer is the number 2, okay? Any question?" "Fine. Take, for example, 2 to the first power equal, anybody?" 2, good. 2 square equal 4, okay, fine. 2 to the third power, that not 2 times 3, that 2 times 2 times 2 equal, anybody? 8, good. 2 to the fourth power equal 16. 2 to the fifth power equal 32. And then 64, okay, fine. Think your RAM, okay? Think computer RAM. 256, 512, 1024, okay, fine. It was so cool. It was so great. So from his little endeavor in that. That's where I realized about zero powers and about negative powers. Let's look what happens when you go this direction. What's happening from the number 2 to the 4 to the 8 to the 16 to the 32? What's happening? It's doubling. Is that fair? So heading in that direction, we are effectively doubling the number because it's the number 2 that we started with. Well, a lot of times in the English language, we read from left to right. In Asian languages, did you know that they read from right to left? If you ever pick up a magazine in Japan, it's backwards and it's upside down. So let's go this way. From the number 8 to 16, or from 16 to 8 and 8 to 4, what's happening there as we go to the left? The opposite of doubling, the inverse of doubling. There's no verb for it, but I'm going to make one up. Double downing? Is that like Mrs. Downing? Cloned? Yeah. What if we cut something in half? Is it fair enough to say halving? Can I write it backwards? H-A-L-V-I-N-G. Halving? Does that make sense? That we're cutting the thing in half? You with me so far? Okay. So let's go to the next step in this phase then. All the powers were 4, 3, 2, 1. What's the next power going to be? 0. So we're going to take the number 2 and we're going to divide the number 2 in half. We're going to cut it in half. And what is half of 2? 1. Oh! It makes a little bit of sense now, doesn't it? And then let's go to the next one. It would be 2 to the negative first power, right? What are we doing? We're taking the previous number and cutting it in half. What do you think? Does that make a little bit of sense about how negative exponents work? Good. What did you think of that college professor? Could you have stand at his class? It was awesome. I liked it. All right. Real quick trivia question. If Mr. Bartz ever asks you, how many kilobytes in 1 megabyte? Question mark. Everybody thinks it's 1,000, and it's not. It's close, but close only counts in horseshoes. It's 2 to the 10th power. So let's keep on going. 2 to the 6th is 64. 2 to the 7th is 128. 2 to the 8th is 256. 2 to the 9th is 512. So 2 to the 10th is 1,024. There are 1,024 kilobytes in 1 megabyte. Because in computers, everything is power 2. Okay, fine. So we've talked about real number properties. I feel pretty good about those. I hope you do too. What we need to talk about next is how to solve a linear equation. Solving, and we're just going to look at some basic linear and quadratic equations. Now, I'm going to let you in on a little secret, something that I don't know why they wait until Algebra 2 to teach you. This is the silliest thing ever. There's this thing called the FTA. Now, F stands for what you do the first week of basketball when you dribble up and down. And fundamentals, yeah, you got to have a good foundation in the fundamentals of a sport or a thing. So this is the fundamental. And then in math, you know that there's these certain ideas that can be proved true that you learned about in geometry. Pythagoras, I think, had a famous one. Theorem. There's this thing called the fundamental theorem. The little O stands for of. And then what class are we in? We're in Algebra 2, and this is of algebra. Have you ever heard of this? The fundamental theorem of algebra? Why do they wait till Algebra 2 to tell you this? This is going to blow your mind. You ready for this? What it says, this is awesome. It says this. It says equations have solutions. Duh! Solve this equation. Yeah, my answer's the solution, of course. That's why they don't tell you, because it's your sophomore, junior year, and you got to have something silly to learn. Why do I have to go to school 178 days to learn about this? This is the dumbest thing I've ever heard. Well, it's corollary. It's corollary. It's corollary. I might have got carried away. I don't know if there's two R's in it or two L's in it or two more R's. I don't know. I probably spelled that wrong. I'm going to put spelling question mark. Somebody let me know if they figure out the right way to spell. I think just one R on the back end of that. Its corollary says an nth degree equation has n solutions. And we'll clarify this a little bit more as the year gets further and further into it in chapter 5. But it says an nth degree equation has n solutions. Now my advanced class, my Algebra 2A class, they took a quiz on the first day of school. And they were asked to solve an equation, and not a single one of them got it right. And that was a pretty easy equation to solve. So we're going to look at that, keeping in mind what the corollary to the fundamental theorem of algebra says. It says an nth degree equation has n solutions. Now, you're probably saying, Mr. Minnick, what the heck's this nth degree business? Well, if we have x plus 8 equals 12, the degree there, let me highlight a few things. The degree is simply the largest exponent that shows up. What's the exponent on that variable? 1. Nice. The exponent on that variable is 1. So the degree of that equation is 1. So the fundamental theorem of algebra says that this thing is going to have how many solutions? 1. You with me so far? Okay. So here's the equation that I gave them. I said, solve 4x squared equals 100. Now, we are talking about how to solve basic equations, and I don't know if your algebra teachers made this clear, but I'm sure you've heard of PEMDAS. PEMDAS is used to evaluate expressions. This is what you use to evaluate. That means to simplify or get the answer. When you solve an equation, you're kind of working backwards to the variable, and you're undoing that evaluation process, and you're going to use SADMAP, if that makes any sense. You're going to do the order of operations in inverse order to get back to the variable. When I taught regular integrated math, I used to say this, and I got myself into a little bit of trouble. I said, you want to get this variable, you want to pretend like that's your girlfriend, or like that's your boyfriend. You don't want your mom around, you don't want your dad around, you don't want your friends around, you want that thing all by yourselves. So we got to isolate the variable. So what's the first thing we need to do to get that x by itself? We want to add or subtract. There's no adding or subtracting, so then we're going to divide. We divide by what? 4. So 4 divided by 4, we know that those cross cancel, and that makes an x squared on the left. And everybody knows that 100 divided by 4 is 25, I hope. All right? So then we say, okay, is there any multiplying? No. Are there any exponents to handle? Yes. How do I get rid of squaring something? Square root it, or take its square root. Okay? So when we do this, we need to go ahead and take the square root of this. And we take the square root of this. Now let's think back for a minute. What is the degree? What's the degree of this particular equation? 2. So we know that the degree of this thing is 2. So how many solutions, according to the fundamental theorem of algebra, should this equation have? It should have 2. So everybody in the advanced class said x equals 5, and they circled their answer, and they were done, and they went home, and they missed it. You're like, but dude, they got half of it. Well, let's think about half. Half's 50%, right? What's a 50% according to our grade scale? Half. So what's the other answer? -5, yeah. The other answer is -5. There's a couple different ways that you could arrive there, and we'll talk about those in chapter 4, but the other answer is -5. While I'm loading my calculator, why don't you take a minute, grab a TI Inspire. I'm going to show you something that's really cool. So today we're going to be solving basic linear equations. Next lesson, well, actually later in the week, Friday, we're going to have a lesson on solving absolute value equations, but I kind of want to show you a sneak peek of an alternative way to solve equations. It's awesome. I wish they showed me this when I was in school. What we're going to look at for our next example is we're going to try to solve this. To solve the absolute value of 2 minus x is equal to 7. Now, I know some of you are probably thinking to yourself, oh, I know what the answer is. You could just say 2 minus x equals 7, so x is -5. And so the answer is 5 and -5. Well, it's not that easy. What I want to show you is 2 different ways to solve this with the calculator. Number one, you can use this technique called NSolve. Anybody ever hear NSolve on the calculator? Did I show you this? It's the bee's knees. It's the cat's meow. It's the horse's pajama. What you're going to do is you're going to type NSolve, left parenthesis, the equation, followed by a comma, followed by an x, because that's the variable you're solving for, and then in parentheses. Okay? So you're just going to type those things. Now our equation is the absolute value of 2 minus x equals 7. So let me see if I can do this. Notice I'm on a calculator page. I'm not using the scratch pad. I'm on a calculator page. So I'm just typing N S O L V E. Watch what happens when the E shows up. See how it's italicized? When the E shows up, watch what happens. See how it's not italicized? The calculator's like, dude, I know this command. Solve what? Absolute value. You got to use the math template button next to the number 9. There's a template, and you'll see your absolute value there. So in the absolute value, I got 2 minus x. I'm going to arrow over, and then I want to set that equal to 7. So I got the absolute value of 2 minus x. And then I want to put a comma x after that. I want to put a comma x after that. Able to keep up all right? Where are we stuck at? To get the absolute value, we use the math template button. After this, press enter. After the x? Oh, well, you need an equal 7. You need your 2 minus x in absolute value, and then you need an equal 7. Let me see what you got going on here. So in absolute value, I got 2 minus x, and then equals 7. There we go. Whoop. And then comma x. There we go. Anybody come up with -5? -5? Anybody got that? So the cool thing is, this gives us the answer. X equals -5. Now, this particular instance doesn't fall into the fundamental theorem of algebra, because the fundamental theorem of algebra applies to polynomial functions. And you might say, well, the degree is 1. Yeah, the degree is 1, but this is an absolute value function. Anybody know what absolute value functions look like? If you graph an absolute value function, if you were to take y equals the absolute value of x and graph it on the Cartesian plane, when you graph it, it looks like this. Did you know that? Because the absolute value of a negative number is positive, and the absolute value of a positive number is also positive. Anyway, there's another way I'm going to show you to solve this. It's probably going to make things so much better. Number two, we're going to use two functions. We're going to use two functions to solve this. What we're going to do when we solve this is we're going to make two functions. We're going to graph f1 of x equals the absolute value of 2 minus x. And we're also going to graph f2 of x equals 7. I'm going to go to a graphing page, and I'm going to graph each half of the equation as its own individual function. And the cool thing about using two functions is my solutions are the x values where the functions meet, where the functions intersect. So if I can get these two functions to intersect in some place, the x values where they do intersect, those are my answers. And we'll take more time. If I'm going too fast with the calculator through this, we'll take more time to do this another day. But I'm going doc, I'm going insert, I'm inserting a graphs page, and f1 of x is the absolute value of 2 minus x. And I can see that V shape. And then I'm going to hit tab, and I'm going to graph my second function as 7. It's a horizontal line. I don't see it because I need to zoom out. I'm going to do a window. I'm going to zoom out just a little bit from up here. And it's pretty clear that those things intersect in two places, right? So if I use my special eyes, I can analyze the graph. I can find the intersection point. One of them is -5. The other one ends up being +9. So it's not -5 and +5. I know I went really fast through that, but what do we think? Is that pretty cool how you can solve by graphing? I think that's a fail-safe way of solving equations. I think it's the bee's knees. I can't believe I showed you that the second week of school. I never do that. Suppose we had to solve this equation. X minus 5, the quantity squared, plus 7 equals 35. Suppose we had to solve that. What should we do first? Remember, PEMDAS backwards. Subtract the 7. Nice, good. So we get x minus 5, the quantity squared, equals 28. Now we're trying to get the variable by itself, but we have this quantity being squared, so there's no more addition or subtraction, there's no more division, there's no more multiplication. The next thing to do is to take care of that exponent, right? So how do we undo squaring a quantity? Don't we square root the quantity? So we get x minus 5 is equal to the square root of 28. Now earlier I mentioned that one property, and you'll see at some point this year that that's going to be 4 rad 7. Nope, that's going to be 2 rad 7. And so our solution set here is x equals 5 plus or minus 2 rad 7. Okay, if that went way over here, don't worry about it. I just want you to kind of get the gist of how to solve equations. I want you to realize there would be 2 answers to this. They're 2 unique answers. They're irrational, but there are 2 answers to this. Okay. Does anybody have any questions so far? We're almost done. The last thing we need to talk about today are variables. The last thing we need to talk about are variables. The variables. There's some variables that are okay. There's some variables that are a question mark, and there's some variables that it's really bad to use. So we'll put a column for each of these. What's the number 1 variable you see in algebra? X. And the next one you see after X? Y. Because I want to know. And then you see Z also, right? I'm going to put Z under the question mark. Why would I put Z as a question mark? What does Z sometimes look like? A 2, right? Sometimes Z looks like the number 2. So that's why I'll put a question mark. If you make the German Z, maybe it's okay. What about A? Is A okay? It's not really bad. What about B? Is B okay? Sometimes a B and a 6 could look alike, huh? The number 6. Some people make their B's weird. I don't know. C is usually okay. D is usually okay. And I know what you're thinking. Well, if D's okay, then E's got to be okay. Well, I got news for you. E is not okay. E is actually a number. We're going to study it at great lengths in chapter 7, but E is a number, so we can't use E as a variable. F's good, and G's good, H is good. And I know what you're thinking. Well, if G is good and H is good, well, what about I? We can't use I. I is a lot of times used, well, it's not a lot of times, it's all the time, it's used to talk about the imaginary unit, the square root of -1. It's a number. It's a complex number. It's imaginary, but we can't use it. So I is actually another number. H-I, J is okay, K is okay, L is okay, M, N. What about O? Yeah. The number 0 and the letter O, yeah, I wouldn't use O. P's probably not bad. Q's not bad. R. S. Is S okay? It's okay, but yeah, S's and 5s look alike, right? So T's probably okay. Well, some T's. Capital T, maybe not. What can capital T kind of look like if you make it, or even if you make your T like this? What's the matter with that? Looks like an addition sign. So maybe T's not so good. U's probably okay. V's probably okay. W, and I think that takes care of the rest of them. All right, that's it. That's today's lesson. I didn't tell any cheesy jokes yet. Do you want to hear one? Knock, knock. Owls. I know. Have a nice day. See y'all later.
Good.